Today's topic, as implied by the previous video, is Hooke's law, stress, and strain. And in the previous two videos, maybe one video if I decide to splice them together, I showed you a relatively simple experiment where we took a spring, loaded it up, and measured how much it stretched. Our data are right here. In case you're wondering from the previous video, I've checked the accuracy of all of those little brass disc weights that I used, and I know that they are all accurate to at least 1/10 of a gram. So I'm quite confident when I say that that stack of three 10-gram weights was indeed 30.0 grams. Probably 30.00, maybe a couple more zeros, but at the very least 30.0 grams is the accuracy. And again, here are the distances that they stretched. Now, there is a basic principle of material science, so basic that it shows up even in physics textbooks, called Hooke's law. And Hooke's law is the relationship between how much you load up a spring and how much that spring stretches. So, let's look at the variables involved in Hooke's law, as well as the actual equation that constitutes Hooke's law. In the equation for Hooke's law, the variables are F, which is the force applied to the spring, which is the same thing as the load. If in the previous experiment, I brought the spring to a stop because when the spring and the weights at the end of the spring are at a stop at acceleration 0, the load and the force applied by the spring are equal to each other. So load, force, same thing. There is L, and I'll write my L's in cursive so we don't confuse them with ones. That's the length of the spring. There is L0, which is the length of the spring, but it's the length of the spring when it is exerting no force. It is what's called the relaxed length of the spring. And sometimes the relationship between L and L0 is summarized in how far the spring is stretched, as I did in my own experiment. So we'll throw another variable in there. Let's call it D, which is the stretch distance. And in case you haven't figured out already, D is equal to L minus L0. In other words, how far the spring is stretched for a given one of these trials is equal to how long the spring is stretched when it's loaded up minus how long the spring is stretched when it's completely unloaded. Now, I happened to adjust the zeroing on the Hooke's law apparatus so that I was measuring D, in other words, so that I didn't have to worry about actually measuring L0, which is why I record my data as how far the spring is stretched, not how long the spring was. You can tell because my initial point is load 0, stretch 0. Okay, so Hooke's law, named after Sir Robert Hooke, a contemporary of Sir Isaac Newton, says that F equals K, that's a lowercase k, times L minus L0. And, okay, so I'm throwing one more thing in that's not on the list of variables. This quantity, K, is called the spring constant. And the spring constant is a measurement of how stiff the spring is. Let me show you a really simple example. Okay, this is a compression spring that I pulled out of my collection. And yes, every physics teacher has a collection of springs. And for such a small spring, it's pretty stiff. You notice how much force I have to put into compressing this spring, not a whole lot. And then if I take the spring off of the Hooke's law apparatus, well, let's actually do this in tension, okay? So, small spring, and here we go, we need a dark background. This suit makes a nice dark background. You put a decent amount of force in, and it doesn't stretch a whole lot. Another spring, put a little bit of force in, and it stretches quite a bit. So, we need one more quantity to relate force to length. And that is the stiffness of the spring, and that is quantified as the spring constant. So, all of that is a really fancy way of saying a higher value of the spring constant means you have a stiffer spring. So, higher values of K mean you've got a stiffer spring. Similarly, lower values of K mean you have a more flexible spring. Now, you'll notice L minus L0, you might have seen that over here. So you can also express Hooke's law as F equals KD or F equals KX. There's a bunch of different variations on Hooke's law. So let's go back to the two example springs, one of which I just dropped. Give me a moment. All right, so we got the flexible spring. Little bit of force, a lot of extension. We've got the stiffer spring, a lot of force, not a whole lot of extension. The key difference between these two springs is that one of them is made out of thicker wire, and the other one is made out of thinner wire. Allow me to illustrate. If you take, it is not due to the material that the springs are made out of. Allow me to illustrate. This is just a simple magnet that I pulled off of the marker board, and the flexible spring sticks to it, the stiffer spring sticks to it, so that means that they're both some kind of steel. Maybe slightly different alloys of steel, but both made out of steel either way. So they should have the same fundamental properties. Scientists, and particularly material scientists, call these intrinsic properties. That is a property that does not depend on the shape and size of the object. So the steel in these has the same intrinsic properties. They get different extrinsic properties, like force, spring constant, and the distance that it stretched, based on the fact that they were formed into different shapes. As material scientists, most of the time, or a lot of what we are doing in mechanical testing, is trying to find the intrinsic properties of a material, usually a metal. And the reason is that we then take those intrinsic properties and do one of two things. Either we try to improve them, or we hand that information off to the mechanical engineers, who then start to take into account shapes, sizes, materials, and other complex variables like that. But neither force, nor the spring constant, nor the distance that a spring is stretched is an intrinsic property. So before we get to something that's really useful for material science, we got to convert these quantities into intrinsic, that is, shape-independent, size-independent quantities. So, if we look at the extrinsic property of force, which, as I previously noted, is abbreviated F, there is a quantity very similar to force, except it does not depend on the shape, nor does it depend on the size. It is called stress. And stress is abbreviated with the Greek letter lowercase sigma. The definition of stress is that it's equal to force divided by area. Specifically, the cross-sectional area perpendicular to the force. So if you have a cylindrical piece of material, like this. Let's forget about springs for a moment, because again, we're trying to get to the fundamental properties of the material, the intrinsic properties of the material. And if we pull it in tension, Newton's third law says you got to pull both sides. Well, actually, no, that's not Newton's third law. It could accelerate. Nevertheless, we pull it equally from both sides. That's our force. If you look at a surface of material, an internal surface of material, that is perpendicular to that force, that area is what supports the force. And this is what allows stress to be shape and size independent. Because if we make this cylinder bigger, we will undoubtedly increase the cross-sectional area. And so, while it might be able to take the same amount of force, it will also have, it might take a larger force, but we would also have a higher area that is spread across, and so you could potentially get the same stress. All right, so stress. It's an intrinsic quantity, similar to force. It's equal to force over area. Let me just throw in a couple notes that are a little less relevant, but nevertheless important when communicating with other engineers. There are actually at least two different definitions of stress. This is the standard definition, and specifically, usually put a subscript 0 right there to say this is the area of the part before we started applying any force to it. As soon as you start applying force, it stretches in this direction and it actually shrinks in the other direction. It's something called Poisson ratio, but we'll get to that later. So, when you define stress as force divided by the unloaded area, that is called engineering stress. When you continuously monitor force when you continuously monitor the cross-sectional area as it shrinks as a result of higher force, then that's called true stress. In my experience, the only group that uses true stress are biomedical engineers. For the most part, mechanical and civil engineers are primarily interested in this definition of stress, which the formal term for it is called engineering stress, but usually it's just called stress. So, stress, formal title, engineering stress, is equal to the applied force divided by the original cross-sectional area. Okay, let's look at an intrinsic version of the distance stretched. Well, as you can probably tell, these intrinsic quantities tend to be two extrinsic quantities divided by each other. So in the extrinsic version of Hooke's law, we had the stretch distance, which was L minus L0. The intrinsic version of that is called strain. Strain is abbreviated, that's a horrible, alright. Strain is abbreviated with this thing that kind of looks like an E, but a little messed up. This is the Greek letter epsilon. And epsilon is defined as L minus L0 over L0. So it's how long the material is right now minus how long it was before we started applying force to it. All of that divided by how long it was before we started applying force to it. All right, and last but not least, we need an intrinsic version of K. In other words, a measurement of not how stiff the spring is, but how stiff the material that we're stretching is, whether that's shaped into a spring or not. In fact, usually it's shaped into a cylinder. We'll get to that in a second. But we have the spring constant, That is an extrinsic property. It depends on the shape and size and the material that the spring is made from. The intrinsic version of that only depends on the material, is called Young's modulus. For reasons that are outside of my understanding, the abbreviation for Young's modulus is capital E. Oh, actually, maybe I do know why this is abbreviated capital E. Sometimes Young's modulus is also referred to as the elastic modulus. That kind of makes sense, right? Must be right. All right. So, if we reformulate Hooke's law in terms of intrinsic quantities, then we can say, we can effectively divide both sides, well, let me see about that. Before I get into quantities that I can't talk myself out of, let me just stick to what I know. All right, so the intrinsic version of Hooke's law is stress is equal to Young's modulus times strain. Let's talk a little bit about units. I think I'm going to have to move this aside a little bit. Here we go. All right, so, okay, so the units of stress is force divided by area. And as a result, the units for stress are the units of force divided by the units of area. Well, there's 3 countries that insist on being rather stubborn and not adopting the metric system. Those are Liberia, Burma, otherwise known as Myanmar, and this little old country called the United States. Because of that last little stubborn country, we have to deal with 2 different unit systems. So the imperial units are pounds per square inch. Otherwise known as PSI. And this should make sense, right? Pounds per square inch is the same thing as a pound divided by an inch squared. In other words, a unit of force divided by a unit of area. Should make sense given the... Okay, so we left off talking about PSI. PSI is pounds per square inch. If we are talking about the way the rest of the world measures stuff, in other words, in the metric system, the metric system unit for force is a Newton. And a Newton is... it's about the weight of 100 grams. So somewhere around here we got close to a Newton of force. Now mass in grams and force are 2 slightly different things. So let's not get that too confused. But the units are newtons per meter squared, or the abbreviation for Newton is capital M, and then the abbreviation for meter squared is m squared. So this should not be too surprising that we have units of force divided by units of area again, because the units have to be consistent with the calculation. However, the term newtons per meter squared is a bit of a mouthful, so this is commonly abbreviated a Pascal, PA. It is one of the few abbreviations in the metric system that is more than 1 letter long, fun fact, and 1 Pascal of stress is a minuscule amount of stress. So you'll often be expressing stresses and other quantities that come in pascals in terms of kilopascals or megapascals or gigapascals. Kilopascals and gigapascals being the two most common in material science. All right, so let's talk about the units for strain. Well, the units for strain are, if you look at the top of this calculation, the units of length, because when you subtract a length from another length, you get yet another length, divided by the units of length. In other words, inches divided by inches, or meters divided by meters. Well, your basic understanding of high school algebra, x over x is 1. It's unity. It's usually not worth mentioning because it's when you multiply by 1, you don't change a value. So, just the same way in a fraction x over x cancels out, units do the same thing. Inches over inches cancels out. Meters over meters cancels out. So strain, the units of strain are no units at all. It is what is called unitless. And if it's unitless in imperial, it's unitless in metric as well. So you don't have to worry about units for strain because your units actually cancel out. Last but not least, your units for elastic modulus. We'll just kind of pretend that that falls in line with the columns here. All right, so since the units for elastic modulus have to be consistent with this equation, let's do a little bit of algebra here. Let's transform this a little bit and isolate E. So we got stress over strain is equal to the elastic modulus. Okay, so the units for elastic modulus must be the units for stress divided by the units for strain. So the units for stress are psi in imperial and pascals in metric, and the units for strain are unity, nothing, well, not nothing, nothing implies 0. So pounds per square inch divided by 1 is still pounds per square inch. Pascals divided by 1 is still pascals. So the units for the Young's modulus and the units for stress are the same. Okay, so we've taken care of explaining stress, strain, the mathematical relationship between them, and the units involved in actually measuring all of these quantities. So now let's do two things. Thing one, let's look at our original data. Let's see if our original data is consistent with the macroscopic extrinsic version of Hooke's law. Well, what this tells us, and it's a little more apparent in this formulation, is that force and the distance that you stretch are proportional to each other, which should mean two things. One, and this is true for all proportionate quantities, thing one is that when the force is 0, then the distance that you stretch is 0. And we indeed show that that is true. And second, whenever you're talking about non-zero forces and non-zero distances, if you double the quantity on one side, you have to double the quantity on the other side. So if we start with 30 grams of force, or grams of load, we have a distance stretched of 1.55, and if we double that up to 60, we almost nearly double the distance stretched. And same thing when you go from 60 to 120. Double the load, double the stretch distance. Triple the load, triple the stretch distance. So, our data are consistent with Hooke's law. Sorry, just had to check to make sure the camera is still recording. Second thing is that we have to express what we have to remind ourselves that all formulas have limits on how far they are applicable. If I was to take this spring and put a heck of a lot of force on it, I would stretch it to the point where it would not come back to the same shape that it started in. That's called plastic deformation. And Hooke's law is only good if you avoid plastic deformation. If you are not having plastic deformation, if your spring or whatever you're talking about comes back to the same shape that it started in, then you have what is called elastic deformation. So, Hooke's law, whether it's in the extrinsic form or the intrinsic form, is only good as long as you're talking about elastic deformation